let's start with the first keynote presentation, which is from Tong. Tong is a partner research manager at Microsoft Research Asia, where he leads the Internet Graphics Group. His research focuses on computer graphics and 3D computer vision and covers many topics, including appearance modeling and rendering, texture synthesis, light transport capturing and analysis, image-based modeling and rendering, as well as 3D learning, facial performance capturing and animation, and 3D graphics systems. He received his PhD in computer graphics from Tsinghua University in 1999, and he regularly serves as paper committee members and area chairs for both graphics and computer vision conferences. He's an associate editor-in-chief of IEEE TV CG and an associate editor of IEEE CG and A, and he has been an associate editor of ACM Tong, IEEE TV.
Good morning, everyone. And in this talk, I'm going to talk about our recent work on modeling and learning 3D structures. I'm sorry that I cannot be on site to give this talk. Many organic objects or man-made shapes in the real world, such as human bodies and faces, as well as the chairs or airplanes shown here, always have very similar structures. So learning these 3D shape structures is an essential task for many graphics and vision applications. In shape completion and reconstruction, the learned shape structure acts as a prior to map incomplete noise observations to complete 3D shapes. In 3D analysis and understanding shown in the middle, the 3D shape structures provide robust features that are independent to the shape details. For geometry modeling, the shape structure provides an efficient way for users to generate and edit 3D shapes. However, learning structure of 3D shape is also a very challenging task. For 3D shapes in one category, they also have their diverse structures, and the space of all shape structures is discrete but not continuous, which is difficult to be learned. Moreover, labeling structure of 3D shapes is a labor-intensive process, which makes the amount of the labeled data for training is quite limited. In the past years, researchers in vision and graphics fields have taken great efforts to enlarge the labeled dataset, develop a supervised method and unsupervised method for modeling and learning 3D structures, which greatly advanced this field. In the past several years, we also did some explorations on modeling and learning 3D shape structures and applied the learned 3D structure in different vision and graphics tasks. So in the following part of this talk, I will present 4 works along these directions. So in these works, we try to answer 2 questions: how to represent the shape structures and how to learn it efficiently from the labeled or unlabeled dataset. The first work I will introduce here is try to learn an explicit 3D structure representation from the labeled dataset and then apply it for 3D reconstruction. The work has been published in CVPR 2019. As shown here, the goal of this work is to develop an efficient method for reconstructing 3D shapes with complex topology structures, especially those shapes with thin structures. Our key observation is that the skeleton provides a good representation of the shape topology and structure. As shown here, a skeleton of the 3D shape is composed of curves and sheets. It can be extracted from 3D shapes by shrinking the surface along the reverse directions of the surface normals. As a result, the skeleton will ignore all shape details and only represent the topology structure of a 3D shape. Based on these key observations, we present a hybrid hierarchical representation for 3D shapes. In particular, as shown here, we model a 3D shape with skeleton for shape topology, discrete 3D volume for all shapes, and a continuous 3D mesh for surface details. Based on this representation, we developed a learning scheme to learn 3 cascaded encoder-decoder networks for reconstructing 3D shape from single-view input image. Here we show the single-view 3D reconstruction results generated by our method and other methods. Note that our method can well reconstruct the scene structure of 3D shapes from single-view input image. Numerically, our method also outperforms most of the existing methods at that time. Here we show some 3D shapes reconstructed from the real images. Finally, our ablation study validates that the learned skeleton representation is critical to reconstruct the scene structures of the 3D shapes. The first work describes how to learn the shape structure for 3D reconstruction. In the second work, we try to learn the shape structure and use it for 3D generation. To this end, we developed a generative model for high-quality 3D shape generation. We want our method not only can be controlled by the users for generated shapes with desired local structures, but also can be generalized to other shape categories that are not in the training dataset. This work will be presented in this year's SIGGRAPH. The key idea of our method is to train a diffusion-based 3D generator that can be controlled by 2D sketches. Our key observation here is that the 2D sketch provides good prior of the 3D shape structures. It can be easily drawn by the user or extracted from a real 2D image, while the 3D diffusion model can be well reproduce all 3D shape details learned from the training dataset. Based on this key idea, we developed a 2-stage diffusion model for high-quality 3D shape generation. In the first stage, our occupancy diffusion model learns to generate a low-resolution occupancy field of the 3D shapes. Then in the second stage, our SDF diffusion model refines the generated occupancy field with a detailed sign disease functions. We also developed a view-aware local attention scheme to control the shape generation by projecting the input sketch to the generated shape volume so that the user can efficiently control the local shape structures via the input sketch. Please see our paper for more details. Here we illustrate the 3D shapes generated by our approach. You can see that compared to existing sketch-based 3D modeling methods, our generative method can generate higher quality results that follow the shape structures specified by the input sketches. Also, as shown on the left, our method can also generate reasonable 3D shapes from the 2D sketch input for unseen shape categories. On the right, we demonstrate that our method is robust to hand-drawn sketches. We just discussed 2 works that learn the shape structures from the labeled data for 3D reconstruction and generation. In the third work, I will introduce how to learn shape structures from unlabeled shape collections. The goal of this work is to learn the shape structure of 3D shapes in a class by shared qubit shape abstractions. We hope this shape abstraction is consistent for shapes with the same structures and can well handle structure variations of the different shapes. For example, if a chair has no arm, we hope that the boxes for the arms are not in its shape abstraction results. Also, we want to learn it from the unlabeled shape collections. So, how we can present the shape abstractions that can meet all these requirements? we have two key observations. While 3D objects in a class have various structures, they share a common structure at a higher abstraction level. For example, the three airplanes here have different structure details, but they are all composed of one single airframe, one tail, and two wings. Secondly, different shapes may exhibit different structure details in different abstraction levels. For example, the tail for airplane has a more fine-grained structure than the airframe. Based on these two observations, our solution is an adaptive hierarchical qubit representation. On the left is the input 3D shape. In the middle is the hierarchical structure of the abstraction. And on the right is the adaptive hierarchical qubit representations. We want to capture as much as possible structure details on multiple levels and get a coherence abstraction at a higher level. Given this hierarchical adaptive qubit representation as target, we need to learn a network to construct its representation from unlabeled shape dataset. To this end, we need to tackle several challenges for a given 3D shape. How many qubits should we use? And what hierarchy should this abstraction follow? Finally, how to optimize the parameters of the qubit? To this end, our solution is to learn a multiple-level qubit representation with redundant number of qubits in each level. Then we learn another tree selection network to get an adaptive hierarchical qubit for each input shape. We use the shape approximation error to regress the box parameters. So as shown here, our solution is an unsupervised learning method. It consists of three components. Given an input 3D shape, we use a shape encoder network to get a latent code. Then, the qubit prediction module decodes the latent code to three levels of the qubit abstraction with a hierarchy structure. Next, the qubit selection module predicts three levels of selection masks represented by binary signals. Using selection masks, a set of qubits are picked from the hierarchy to form the adaptive qubit abstraction. During training, we update the qubit prediction and selection module iteratively to refine the masks and the qubit parameters. And finally, we get a good adaptive qubit abstraction of the input shapes. To train this network, we also design a set of loss functions for each branch. Please see our paper for more details. Here are the abstraction results predicted by our network. In each category, the qubit with the same color are correspondence part in different shapes. The body of the airplane is represented by the blue qubit, and the seat of the chair is represented by the red qubit. We compare our results with the previous work, which is also an unsupervised learning method for qubit abstraction. They use a single-level qubit setting. Without any hierarchy, their method cannot well address structural variations and result in oversimplified abstraction. Here we show structure-based classification results. We cluster all the chairs shown here by their abstraction structures. In the same group, all the chairs have the same structure, while different groups have different structures. Also, the blue qubit represents the chair back, and the red qubit stands for the chair seat. In all three works discussed above, we model the shape structure in an implicit way. In the last work, we try to explore whether we can model the shape structure in an implicit way and learn it from the unlabeled data. The answer actually is yes. Our key observation is that the structure of 3D shapes can be modeled by the part correspondence between the 3D shapes. So if we have dense correspondence between the 3D shapes, the structure actually can be easily identified from one or few examples. For example, for the sofa and the chair shown here, their shared structure such as the legs and back can be easily identified by the point correspondence shown here, while the structure difference of the two shapes can also be identified by the missing correspondence of the points on the sofa arms. So based on this observation, the goal of this work is to learn a representation of the 3D shapes in one class and their dense correspondence. We hope the learned shapes representation can faithfully model the 3D shapes in one category, and the point-to-point dense correspondence can well handle structure variations. Moreover, we hope the representation can be learned from the unlabeled 3D shape collections. Our key idea is to model the signed distance field of a 3D shape as a deformation of a template field shared by all the shapes and then correct it with a residual field. Here we illustrate our implementation with a 2D slide of a 3D chair. Note that the template field shared by all the shapes actually encode all the possible shape structures in the shape collections. The deformation field then models the correspondence between the 3D shape to the template. The correction field actually corrects the deformed template and filter off all structures not in the current shape to get the final shape details and structures. We model the deformation and correction field with one MLP and the template field with another MLP. A HyperNet MLP is learned to infer the parameters of the deformation field for each 3D shape. The three networks are trained from unlabeled 3D data with reconstruction laws and another constraints. Please refer to our paper for more details. Our method faithfully encodes all the 3D shapes and outperforms other deep shape representations, as shown here. Also, based on the dense point correspondence, our method can easily generate shape structures by transferring the point labels from sparse examples to each 3D shapes. Here we demonstrate that our method is better than other deep learning-based shape correspondence methods and can generate better shape segmentation results. Here we show the texture transfer result. You can see that the learned point-to-point dense correspondence between the shapes follow the shape structures and well handle structure variations of the different shapes. For example, you can see that the texture on the arms of the first chair is not transferred to the other parts of the chairs without the arms there, shown on the second. Finally, our learned representations also enable efficient shape editing, as shown here. After the user edits one point on a 3D shape, our method changes the shape to fit the moved point and keeps the basic structure of 3D shape unchanged. To the best of our knowledge, it seems that there are still no other method can do the same editing operations and still keep these rigid or non-rigid shapes structures of the original shape category. I think the four works I presented above have convinced you that the 3D structure is valuable for both 3D reconstruction and 3D generation and many other tasks. However, I think you will also agree that the 3D structure learning is still a challenging task. For different tasks we shown here, we actually carefully designed different repetitions for modeling shape structures and developed different networks and training schemes for learning shape structures from either labeled or unlabeled dataset. Still, there is no unified solution that we can use for all these tasks. Looking forward, we are exploring several things on 3D structure learning. It is unclear whether we can find a unified representation for 3D shape structures and efficient learning schemes that can disentangle the 3D structure from 3D shape details. Also, we are seeking for self-supervised learning methods and networks that can provide a unified framework for both 3D structure understanding and generations. Finally, it is still unclear how to extend 3D structure learning from one shape category we have done here now to all 3D shapes in the wild. And probably the learning from text, image, and video data will provide helpful solutions here. We believe that these challenges are also big opportunities for 3D learning and generation. Finally, we have released our code and data for all the projects presented in this talk. I would also like to thank my colleagues, interns, and our external collaborators for their contributions to the projects presented in this talk. And that's my talk, and thank you for your attention.
Yes, can you please try to come to the microphone and ask your question?
I think this is Jianfei from Monash. Okay, so I have two questions for you. Thanks for the talk. So my first question is, in your third work, you talk about this kind of shape parsing or shape abstraction work. So I'm wondering, like, I mean, what kind of additional application you have in mind? Say, in addition to parsing this kind of shape, do you think about like it can be used for like shape generation? So this is my first question. And then my second question is, in your second work, you talk about this kind of diffusion for 3D. So it seems you change, I mean, between the different 3D formats that are there. So for your first UNet, you use kind of occupancy kind of representation. And then you kind of switch to mesh, right? In order to use this kind of subdivision. And then after you use mesh, then for your second diffusion model, you use you kind of use this kind of SDF representation. So can you share with us, I mean, what's the insights there? I mean, why do you want to sort of, I mean, switch between the different formats? Thank you.
Thanks, Jianfei. Yeah, so I think that there are two good questions. Yeah, great questions. Thank you. So for the first one, I agree with you. Yeah, I think the shape abstraction will provide, in some sense, consistent some qubit representations for all the shapes in one categories. And let me say, I think it's possible for us to use this representation and apply it for shape generation. But On the other hand, we didn't keep exploring along this direction just because we found that finally to obtain the good shape abstractions there, we really need to design a lot of different loss functions and to balance different regularizations to achieve the good result. And in some sense, we meet some difficulty to generalize the approach for different kind of or different shape categories there, in some sense. That's our difficulty. And so we are switched to exploring other possible solutions there. Yeah. But definitely, I think it's possible to say whether the abstract shapes can be used to give you some structural representations and then used for shape generation. For the second question, and I'm sorry that I didn't explain it clearly. So after we obtain the occupancy field, so the subdivision is that we simply increase the resolution of the voxel resolutions there. And after that, we in the higher resolution volumes, we do the diffusion models for the SDF and obtain the shape details. And we separate it as a 2 steps just because we find that if you use a single step, it's so difficult to balance what kind of OO shapes or shape details you should be generated. I think somehow it's quite similar to when the people do the 2D diffusion models, they also use the multi-scale approach to first generate OO 2D image at a lower resolution. Then you have another diffusion model to increase resolution to do the super resolution works. I think we share the similar ideas. Yeah, there. I'm not sure whether I answer your questions there. Yeah, thanks.
If people have more questions, we can have one more.
Thanks for the great talk and presenting such interesting papers. I had a question on your last paper. So from my understanding, you get this dense shape correspondence by through sampling common points on the template shape. I was wondering if you had to do any special kind of regularization to prevent mismatch correspondences during your training.
Sorry, you mean the yeah. Sorry, let me repeat your question to make sure that I hear it clearly. So your question is that whether I use any regularization to avoid the mismatched correspondence in the training process, right?
Yeah, because I guess just to clarify, for example, if the deformation field that you learn sort of takes points from the template to different parts of different shapes that you generate, you have a mismatch correspondence. So I was wondering what you do to prevent that kind of mismatch.
Yeah. Let me say this. Yeah, good questions. In our current implementation, we use this normal consistency constraints, and we found that will help us to give us a better correct correspondence between the different shapes. For example, if we have a car or a chair there, that will avoid some, for example, for the chair, that will avoid some a point on the chair back will map to the chair base on another chairs. Yeah, we found that to be very useful. But I think the key idea here is that we found that to build this shape correspondence between the two 3D shape or two 2D surface there, we actually need to have this correspondence in the whole volume, which means the 3D to 3D correspondence. That help us to avoid a lot of errors or mismatches if you try to build the 2D shape, 2D surface to 2D surface correspondence, just because definitely you will make some mistakes for the missing structures or mismatched parts. Yeah, like some part is missing on the other shapes there. So 3D volume correspondence, by default, you can get the identifier mapping, right, to the same position there. And from that, when you have the more template and deformation field there, always we find that a smooth deformation field will give you a good results. Yeah. Not sure whether that helps to answer the questions here.
Okay, thank you very much. That was a great talk.
Thank you.
If you have any other questions, maybe directly post them on Zoom because we are running really late.